Hello everyone, in this video we're going to see the solution for the HackerEarth problem, removal of vertices. So it is a part of April Circuits 20, it is the fifth problem. So in this problem, and this is a little lengthy one, so bear with me, I'll explain to you the pattern that I saw within the test cases and with that how I got my approach. So basically we give an n-sided polygon where vertices are numbered from 1 to n in clockwise order, and we're given integer k, and we create a explosion machine that explodes vertex in polygon, thereby reducing the size of the polygon. And we start with vertex 2, and at each step one of the following operations on the polygon is performed. So if k is greater than 0, there's no effect, but k is reduced to 1 and we move to the next available vertex at distance 2 in the clockwise direction. When k is 0, then the vertex starts exploding, and polygon with vertex 2 and 1 exists. So we can see from this example. So n is equal to 4, k is equal to 2, and so we have to find the last vertex which is remaining. So in this example they've explained n is equal to 4, meaning we have a polygon of 4 vertices, 1 2 3 4. K is equal to 2, and always we start with the vertex 2. We start with the vertex 2. So we've started with 2 and k is equal to 2, so no effect on 2. We move to the next, so 4, k is equal to 1. Now we again no effect because k is greater than 0, then again we move to the next, so 2. Now k is equal to 0, 2 will explode. 2 will explode meaning 2 is no longer there. So we have 1, 3, 4. Now we come to 4, there's explosion on 4, we come to the next vertex. So 4, 1, 3, we come to 3. And then 3 is exploding, 1 is remaining. So like that we have to find for given n and given k what is the last vertex remaining. And if you look at the test case, it is 10 to the power 14, right? So you cannot even put one loop because that will mean 10 into 10 to the power 14, which will give you 10 to the power 15, which will need a lot of time, and there's only 5 seconds for each input file. So I'll explain to you what I did, and so let's get started. So first, the intuition that I got is, well, let's just see some examples randomly. So say for 6 itself, n is equal to 6, n is equal to 6 and k is equal to 3. So meaning that for 3 times we have to keep moving because now vertices won't be exploding. So I'll write the vertices. So we have vertices 1, 2, 3, 4, 3, 4, 5, 6. We start from 2. So k is equal to 3. So from 2 we move to 4. From 4 we move to 6, and then 6 we move back to 2. And when I come back to 2, now k is 0. So now vertices will start exploding. So first thing to find is when k is equal to 0, where is the index, right? So we'll be doing this in two parts. If n is even, so if n is even, why am I doing it in two parts? I'll just show you in a second. So if n is even, suppose I have 1 2 3 1 2 3 4 5 6 7 8. This is my polygon. You can think of it as a clockwise. So if n is even, and suppose k is equal to anything, k is equal to say 13. So if n is even, I'll go from 2, I'll go from 4, and I'll go to 6, I'll go to 8, and again I'll come back to 2. So if n is even, for each k, I'll be moving among the even vertices only. So say k is equal to 5, and say n is equal to 8. And as it says, I start from 2. So starting from 2, then I come to 4, then I come to 6. So k is equal to 0, I'm at 2. K is equal to 5, I'm at 2. Then k is equal to 4, I'm here, then I'm here, then I'm here. So basically what we have to do is we have to find the position where it will be with the given k. So it's very simple. First, I find a variable, say a variable even, which will be n by 2 obviously, the number of even vertices. So only among the number of even vertices like 2, 4, 6 and 8, the index will be no matter for what k, because it will keep rotating between 2, 4, 6, 8. From 8 again it will come back to 2, again 4, 6, 8. And at every, if k is equal to even, so if at every even it will come back to itself. How? So I'm at 2, first I move to 4, second I move to 6, third I move to 8, fourth I move back to 2. Okay, so I do if k is greater than, or let's just simply say k is equal to k percent even. So this will be doing all the rotations for me. So suppose if k is 8, k is 8. So at k is equal to 4, I'll come back to 2, k is equal to 8, I'll come back to 2. Or suppose k is 9. So I'll be moving from k is equal to 0 to k is equal to 9, which is the same as moving from k is equal to 9 to k is equal to 0. K is equal to 0, I'm at 2, k is equal to 1, I'm at 4, k is equal to 2 at 6, k is equal to 3 at 8, k is equal to 4 at back on 2. Then again at k is equal to 8, I'm back on 2, plus 1, 4. So at k is equal to 9, I'll be at 4. So which is why I'm doing k is equal to k percent even. So when k is equal to 9, k is equal to 9% 4, which will be 1. And after I do k is equal to k plus percent even, 2 plus 2 into k. So this will be the index which I'll be at. Index is equal to 2 plus 2 into k. And we have to make sure that this doesn't go beyond n. So index at even, at whether n is even. So for n is equal to even, a found index is the index at the, say, pointer. The explosion I'll say at pointer will be when k is equal to 0. I had to pause because of some noise in the background. Yeah. So index for me is right now is the index at the pointer, index where the pointer will be, let's say index where the pointer will be when k is equal to 0. So right now I found the index where I'll be starting the explosion from if n is equal to even. I'll move on from that, but let's do what if n is equal to odd. So let's take n is equal to 5. So I'll have 1, 2, 3, 4, 5. So suppose I move from 2, I move from 4, and from 4 I'll come to 1, so I'll come to 3, I'll come to 5. So in the even, when as n was even, we, I'll just write it down again, 1, 2, 3, 4, 5, 6. So when n was even, I kept on rotating between 2, 4, 6, 8 itself. So when k was non-zero, at k is equal to 0, I would be only between 2, 4, 6 or 8, because it was like that. But here, when k is equal to 0, I can be at any of the position. So let's do the same thing. When does it start rotating? So I start from k is equal to 0. Whatever k is, suppose k is equal to 5. Let's say k is equal to 5. So I start from 0, k is equal to 0, I'm at 2. As I said, moving from k is equal to 0 to 5 is the same as moving from 5 is equal to k to 0, which we are essentially doing in the question. We have k greater than 0 and we are making it 0 by moving along. So I'm taking k as 0 and I'm making it whatever it was by moving along. So k is equal to 0, I'm at 2, k is equal to 1 at 4, k is equal to 3 at 1, k is equal to 4 at 3. Actually no, let's start again. Yeah, k is equal to 0, I'm at 2, k is equal to 1, I'm at 4, k is equal to 3, I'm at 5, and then the next I'm at 2. So this gives me that I'll be rotating after every fifth. Like here I was rotating after every even. So that's why I did k is equal to k percent even. But here as you can see I'm rotating after every k itself. K is equal to 0, 2, k is equal to 1, k is equal to 2, k is equal to 3, k is equal to 4, k is equal to 5. So if k is, when k becomes n, I rotate back to 2. I, let's say, pointer comes back to 2. Okay, so at every multiple of k, I'll be coming back to 2. Here I'll do k is equal to k percent n. And then basically the same thing, k is equal to 2 plus 2 into k. But if k is greater than n, then k is equal to n minus k. Because there might be the case that I'm at here and I come to 6. So it is not actually 6, but it is 6 minus 5, which is 1. So actually this is index. This is index. The index at which the pointer will be. So if index is greater than n, then the index at which I'm going to be is n minus index. Yeah. So right now again I found out the index is equal to the index where the pointer will be when k is equal to when k is equal to 0. So for both the even and odd, I found the index at k is equal to 0. So now k is equal to 0 and I have the index where I'll be starting from. So again, let me just show you one pattern. So from even, so suppose I have 1, 2, let's remove this for now. So suppose I have 1, 2, 3, 4, 5, and if you're not able to visualize it, you can just draw it in a circular fashion. You don't need to draw a polygon, you can just draw it in a circular fashion, clockwise 1, 2, 3, 4, 1, 2, 3, 4, like that. Yeah. So suppose I have 1, 2, 3, 4. Suppose I'm starting from 2. I'm not starting from 4, I'm starting from 2. So I'm starting from 2 itself. Suppose n is equal to 4 and k is equal to 0 given in the question. So k is equal to 0, meaning that I don't need to travel anywhere. Index is 2, I'll be starting from 2 itself. And n is equal to 4. Index meaning the number itself, yeah. So I'll be starting from 2 and n is 4. So from 2, 2 will explode. Then 2 has exploded. I'll come to 4. 4 has exploded. Now I'll come to 1, 2, 3. 3 explodes. I get 1. So when I started with 2, I got 1. What happens if I start with 4? So I start with 4. 4 explodes. 2 explodes. Come back. 1 explodes. Yeah, I'm sorry I had to pause again. I had a phone call. Yeah, so n is equal to 4, k is equal to 0. So I got, yeah, so I was that if I start from 4, so let me just write down my observation. I start from 2, remaining vertex last say is equal to 1, and start from 4, last is equal to 3. So there's a pattern you can see for 1, 2, 3, 4. So if I start from 2, I'm getting back to 2 plus 1, 3 plus 1, 4 plus 3, 1. And if I start from 4, again the same thing. 4 plus 1 here, plus 1 here, plus 1 here. So what my point is that, suppose I start from 2. Let me just write that down. So suppose k is equal to 0 only. Suppose k is equal to 0 only, meaning I start from 2. Meaning explosion starts from 2 itself. 2. So the last remaining vertex is equal to say r. So r minus 2 will be the difference, which will be common no matter where I start from. So I don't think that was very clear. Let me just take one more example. So I have 2, 3, 4, 5, 6. Okay. So I have this. Now I'm starting from 2. So I start from 2. 2 is done. 4 is done. 6 is done. Okay. And then 3 is done. 1 is done. 5 is remaining. So this was n is equal to 6, k is equal to 0, starting from 2. So I got 5 as the last. R is equal to 5. So I started from 2. So R minus 2 is equal to 3. So meaning that 3 is the difference between the starting vertex and starting index and the last index. This will be common. So I'll just show you. So this was k is equal to 0 starting from 2. So suppose n is equal to 6, k is equal to 1. So I have 1, 2, 3, 4, 5, 6. So k is equal to 1. So k is equal to 0, I'm at 2. K is equal to 1, I'm at 4. So from 4 the explosion starts. So from 4 the explosion starts. So how does it work? 4 explodes, 4 explodes, 6 explodes, and 2 explodes, 5 explodes, and 1 explodes. So which is remaining? 3 is remaining. So R is equal to 3. And that is the same difference if I write it down. Yeah. Actually 3 won't be remaining. Let's do that again. Yeah. It's a little hard to do because it's linear and not a drawing. So I start from 4. So 4 explodes, 6 explodes, 6 to next is 2, 2 explodes, 5 explodes, yeah, and 5 to next is 3, 3 explodes, yeah, so R is 1, 1 is remaining, and so 1, 2, 3, 4, 5, 6. So I started from 2 and I got 5, which had a difference of about 3. So plus 1 plus 2 plus 3. So I started from 4 and I got 1, which had a difference of what? 1 plus 2 plus 3. So my point is that if uh, explosion starts from 2 and last vertex, remaining vertex is equal to R, so difference, which is R minus 2, will be common. So starting index plus diff will give me the last remaining vertex for any case. Which will be index plus difference. So I have to calculate the difference, meaning that if I start from 2, then where the last remaining vertex will be. And this will be there for odd also. So if you find out the difference, meaning that difference is start from 2, the explosion start from 2, and last remaining vertex is equal to R, then R minus 2 is the difference. Then last remaining vertex starting with index I, starting with index, as we have calculated index where the pointer will be index plus that difference, because the difference will be common. So last remaining vertex will be index plus diff. I hope that you've understood this much. I know it's a little confusing. Now, so the point that I've made is that right now, what have we done so far? We have calculated the final index where we will be when k is equal to 0. So for even, I find out the index where the explosion will start when k turns 0. For the even, I've done the same thing, which is the here, which is the pointer will be, meaning the explosion starts when I make k is equal to 0. And now I'm saying that you find the last remaining vertex from 2 and the difference of that and 2, just add it to the index that you found and you'll get the answer. So I'll just show you the test cases which I saw, and I'll just like give some custom input and I'll show you. So suppose I take even cases only. So 4 and 0 because I only want to know starting from 2 where I'll be. So 0 and 6 0, 8 0, 10 0, 12 0, 14 0, 16 0, 18 0, 20 0. How much is that? 1 2 3 4 5 6 7 8 9. One more. 22 0. So I'll just show you what happens in this. The pattern. Yeah. So let's just look at the expected correct output. So it is like 1 5, then 1 5 9 13, then 1 5 9 13, and so on. So what is happening is that the answer for every power of 2 is 1. For 8 it is 1. For 16 it is 1. For 32 it will be 1 also. I'll just show you. 32 and 0. See, for 32 it is 1. So what we'll be doing, and for the next, so and for 6, the answer is 5, meaning that plus 4, and for 8 the answer is again 1 because it is divisible by 2. For 10 it is not divisible by 2, so plus 4, 12 plus 4, 9, 14 plus 4, 13, 16, again back to 1. And this is the last remaining vertex. Last remaining vertex is decided by this pattern for even. So let's go back to even. So for even, basically what the thing is that for n, find the last power of 2. Example, say n is equal to 12. So the last power of 2 before this is 8. Then n minus last power of 2 by 2, meaning its position from the last power of 2 by 2 into 4, and 1 to that, 1 plus that is the last remaining vertex. Last remaining vertex starting from 2. So let's go on, move on this example. N is equal to 12, last remaining vertex is 8. 12 minus 8 is 4, and 12 minus 8, 4 by 2 is 2. So 2 into 4 is 8. 8 plus 1 is 9. For 8, the answer is 9. You can see here also it's what, 9. And if I take this as 6, so if I take this as 6, yeah, so if I take this as 6, the last remaining vertex for me is, actually for 12 it will be what? For 12 it will be 9, yeah, and 14 it will be 13. For 8 it will be, yeah. So let's see for 6 if a formula works or not. So for 6 the last power of 2 is 4. So its position from the last power of 4 is 6 minus 4 by 2, which is 1. So 1 plus 1 into 4. So that gives me 5. So last remaining vertex is 5 for 6. So this formula you have to use for the even part for finding into 4, for finding the last remaining vertex. And once you find the last remaining vertex, you add that to your current index and you'll get the answer. I'll also show you my code within a minute. Actually, this is all to be done in the even part. This is for the even part. So for the even part, simply for n you find the last power of 2, and from that last remaining vertex is equal to 1. plus the number minus last power of 2 by 2 into 4. Then uh, yeah, answer is equal to index plus the last remaining vertex minus 2. The difference, as I said, the difference will be common. And make sure that you know the answer is between n. If it is more than n, just circle it back using modulo or something. So this is for the odd. So this is for the even. And I'll show you my code also. Now for the odd, I have to do the same thing. So again, you can take a look at some examples. It's better to just uh, take a lot of test cases because I was able to see this pattern. I wasn't able to find the reason correctly, but I was able to see that yeah, this test case is happening. So here a similar thing is happening. So here I'll be taking only the odd test cases. So 3, say 5, say 7, say 9, say 13, 15, 17, 19, 21, 23. So here it is starting from 3 and at every power divisible by 2 plus 1. For example, 4 plus 1 is 5, it becomes 3 again. And 8 plus 1, 9, it becomes 3 again. Then again it follows the pattern 3, 7, 15 and like that. So for that basically what the formula is, I'll just show you from my code itself. So this is my code. So as I said, for the even is equal to n by 2, index is equal to k percent even, and index is equal to 2 plus index. So this gives me final index where the explosion starts from. Okay, now LLK is equal to 4, and if k into 2 less than n, then k is equal to k into 2. This I'm doing to find the like power, the largest power before it, or the power of 2 before it. So k will be the power of 2 before it. So b is equal to 1 plus 4 into n minus, as I said, power of 2 before it by 2. And index b is equal to b minus 2, and index is equal to index plus b gives me the answer. And as I said, if it is greater than n, then we need to circle back. That's why I'm doing index is equal to index minus n. Now, for the odd part, as you can see, I found the power of 2 plus 1 just before it. For example, if at 5 it is becoming 3 again, and at 9 it is becoming 3 again. So the power of 2 plus 1 is happening here. So the same thing, the greatest for the odd is, this is the odd. Greatest power of 2, k, let's say I find k equal to power of 2 plus 1. The greatest power of 2 plus 1 before it. So find the greatest power of 2 before it, add 1 to it. Greatest power of 2 before it, because it is odd. Add 1 to it and then do the same thing but with 3 here. So 3 plus 4 into n minus k by 2. And I'm doing b is equal to b minus 2 because as I said, we have to take the difference. So this b is just simply the difference. So b is the last vertex and minus 2, I'll get the difference, and I'm adding that difference to index. So again, in a nutshell, what I'm doing, I'll just explain to you again. With this even, I'm finding out where the final index from where the explosion starts from, which is at index. Then I'm finding out if I start the explosion at 2, where will I be? And that is B. The answer for that is B. And for B, I'm doing B is equal to B minus 2. So B is equal to B minus 2 and I'm doing B is equal to 1 because if B is equal to 1, then B minus 2 will be 1, then simply it will be index minus 1. The same thing. So b is equal to b minus 2, index is equal to index plus b, because this is the difference, and add the difference to the index, you get the answer. Same thing for the odd. Same thing for the odd. Index is equal to k modulo n to find out the rotations, and index is equal to 2 plus index into 2. So now again the same thing. Index is the vertex explosion starts from, vertex where explosion starts from. Then I found the greatest power of 2, which is divisible by it, and then I add 1 to it, and then 3 plus its position from uh, the plus power of 2 and minus k by 2, then this the difference, and add the difference to 2. So this was my approach. I know it was like very lengthy, and even for me it took a lot of time, because I had to search for a lot of test cases. So this was my approach. I know it was a little confusing. So if you have any doubts, or if I missed out something, or if you think that this could be done in a better way or easier way, then feel free to write it in the comments. And if you have any doubts or confusion, just write it in the comments. I'll be sure to answer. Thank you.